Hi everyone, my name is François Mazet. Today I am going to present the work that I carried out in the Decode lab at MIT, advised by Professor Faiz Ahmed. The associated paper, entitled Diffusion Models Beat GANs on Topology Optimization, introduces a new diffusion model, Topo Diff, to an engineering design field. To start off the presentation, let me introduce topology optimization. Imagine you have a beam made of metal, wood, or any material. This beam is subjected to forces represented by this arrow and to boundary conditions represented by these icons that prevent displacement in one or more directions. Now let's assume that you want to remove 60% of the material, hence this volume fraction of 40%. Topology optimization aims to determine where to remove material and where to keep it so the structure has the best mechanical properties. In practice, the physical metric that we try to minimize is usually compliance. On the image on the right, you can see the optimal structure for these input conditions. So why do we care about this problem? Well, it turns out that topology optimization is vital in many engineering domains, like aerospace engineering and mechanical and civil engineering. The main reasons include the fact that optimizing a structure reduces the manufacturing cost. It also reduces the weight of the structure, which is absolutely critical, notably for aerospace engineering. All of that while ensuring good physical performance of the generated designs. Recently, topology optimization has gained even more attention with the recent advances in 3D printers and additive manufacturing. Highly complex topology optimization generated designs like this one or this one now become manufacturable and thus transform the physical theory into practical applications. This is why most professional design software, such as Autodesk's Fusion 360 and SolidWorks, now include topology optimization features. So, what are the usual methods to solve topology optimization? The most widely used method is called SIMP, for solid isotropic material with penalization. The idea is to start by dividing the domain into elements and assigning a continuous density to every element of the mesh. This density ranges from 0 for void to 1 for fully filled material. Then the physical properties are computed, and notably global compliance. Eventually, the density map can be optimized by computing the gradient of compliance with respect to the density. Now, a problem that we face is that intermediary densities usually make little to no physical sense. To address this issue, penalization and filtering are added, thus avoiding intermediary densities. This traditional method is prone to two major pitfalls. Firstly, penalization and filtering make this problem non-convex, causing the optimization to get stuck in local optima. Additionally, the SIMP method is computationally expensive and therefore takes a lot of time. These issues have been motivating researchers to develop alternative data-driven methods to solve topology optimization. Using GANs is one of these methods. Generative adversarial networks are a type of deep generative models which have shown outstanding performance in image generation. GANs are able to generate extremely realistic images of human faces, for instance, thus proving their ability to automatically extract knowledge from data. Some models, like DALL-E, are even able to generate an image corresponding to a specific prompt given as input. So the idea driving research in this field is to apply these generative abilities to engineering design. Recent work in data-driven topology optimization has focused on GANs. Two approaches have mostly been developed. The first one involves using a CNN to generate low-resolution solution, and then passing the output through a GAN to increase the resolution. The second approach, which is the most recent state-of-the-art approach, consists in using a conditional GAN to generate the optimal topology when given as input a representation of the constraints. On the right, you can see some results obtained from Topology GAN, a conditional GAN corresponding to this second approach. The results are very promising, since the GAN has clearly been able to capture some key aspects of topology optimization. However, the model often generated unmanufacturable designs and seems to struggle a lot more when given input constraints with out-of-distribution boundary conditions. In the end, using deep learning for topology optimization faces several challenges, among which the lack of data, the need to condition models with a complex type of data, which are physical constraints, the need to adapt usual evaluation metrics, since MAE and MSE do not matter for physical problems, and the fact that deep learning models usually try to mimic training data and neglect physical performance and manufacturability. Hence, our hypothesis is that a performance and manufacturability explicit guidance is necessary. This is what we introduce in Topo Diff. Topo Diff relies on a rather recent type of deep generative models, diffusion models. We chose to explore diffusion models because they are easier to train than GANs, because they were recently shown to outperform GANs for image generation in terms of sample quality, and because their sequential sampling process makes it possible to include external guidance. The main question that our work addresses is, therefore, can diffusion models also outperform GANs on topology optimization? Before going into the details of how Topo Diff works, let me introduce briefly the concept of diffusion models. Imagine you have a noising process that allows you to transform a clear image into a fully noised image. In order to do so, we can use a Gaussian Markov chain, for instance. Now, imagine you can learn to reverse this process. That is to say, learn a denoising process. Then, to generate a new clear image, you just need to sample from a white noise distribution and then denoise the image with the learned denoising process. This is the idea behind diffusion models. In practice, the denoising process can be represented as a Gaussian process as well. Training a diffusion model thus amounts to training two neural networks on noisy data, one predicting the mean of the denoising Gaussian distribution, and one representing the variance of the denoising Gaussian distribution. Note that these neural networks need to work on all levels of noise. To generate a new image, you then just need to sample from the predicted denoising distribution at every step of the process. Now, this is the general principle of diffusion models, but how can we include conditional information like boundary conditions, loads, volume fraction within such a framework? The first conditioning strategy that we include in Topo Diff is to add constraints as extra channels to the input image. At every denoising step, instead of solely passing to the network the image that needs to be denoised, the input consists of the image, the loads, the volume fraction, and physical fields that are stress and strain fields. But this strategy alone is not enough and would be prone to the same issues as the GAN models introduced earlier. We thus add an explicit guidance strategy. Topo Diff includes two surrogate models to perform this guidance. The first surrogate is a regressor that predicts the compliance of a given topology. The second surrogate is a classifier that detects floating material and outputs the probability that the topology contains floating material. Note that these two surrogate models need to work on clear and noisy images. These surrogate models are used to modify the denoising distribution by penalizing high compliance and infeasible designs. Imagine the denoising distribution is this green curve, and the distribution of probability for floating material is the blue curve. Classifier guidance, initially introduced by Dhariwal and Nicol, consists in multiplying the two curves to obtain the red curve, from which we sample. In addition to classifier guidance, we introduced regressor guidance, which works the same way, with the blue curve representing this time a function which is close to 1 when compliance is small, and close to 0 where compliance is large. Let's add this guidance strategy to our conditional diffusion model. It can easily be proven that modifying the sampling distribution amounts to shifting the mean of the denoising distribution, both for classifier and regressor guidance. We refer you to the paper for more details. To test Topo Diff, we introduce a dual-level test dataset. Level 1 and Level 2 contain new combinations of constraints and therefore new topologies. But Level 1 contains in-distribution boundary conditions, whereas Level 2 contains out-of-distribution boundary conditions. To replace MAE and MSE, which do not matter for topology optimization, we introduce 4 meaningful metrics. The compliance error quantifies how much better or worse the generated topology is compared to the topology generated by the traditional SIMP method. The volume fraction error quantifies the gap between the prompted volume fraction and the volume fraction of the generated topology. Load violation checks if material is present where a load is applied. Here, the left image is okay, but the right image contains a load violation. Floating material eventually checks if the topology contains floating material, which would cause unmanufacturability. Here, the left image is okay, but not the image on the right, because of this. Compliance error evaluates performance. Volume fraction error and load violation check the respective constraints, and floating material checks the manufacturability. Here are a few qualitative results on both test datasets. For every sample, the image on the left was generated using state-of-art GAN model. The image in the middle is the one obtained with traditional methods, and the image on the right was generated by Topo Diff. As you can see, Topo Diff seems to be able to generate good performing structures on both datasets. It also produces significantly less floating material than the GAN. To quantify these observations, we show here the results on the full test datasets. Topo Diff outperforms the state-of-the-art GAN on all metrics. We also conducted an ablation study to confirm the impact of our guidance strategy. The floating material guidance has a positive impact on both test datasets. The compliance guidance has no significant impact on Level 1 test data, but has a clear positive impact on Level 2 test data with out-of-distribution boundary conditions. To wrap up, we introduced Topo Diff, a new diffusion model for topology optimization that outperforms state-of-art GAN. An essential part of Topo Diff is the guidance strategy that actively favors structures with good performance and good manufacturability. More generally, this work shows that diffusion models have the potential to outperform GANs also on physical optimization problems. Our work suggests a general framework that can be used to solve other physical problems. Thank you so much. Feel free to reach out for any question you may have.